So let's take a look here at examples number 3 and 4. I want to find here all of the different values of c that satisfy the mean value theorem for integrals for the function f of x equals 1 plus x. Notice this was the example that we looked at actually back in example 1, or this is the function that we looked at in that example. And we saw that back in that example, if I was to go and scroll back to it, that we found that our average y value for this graph on the interval from 0 to 3 was going to be 2.5. And the mean value theorem for integrals states that as long as my function is continuous, and this function is definitely continuous, right? It's a polynomial. As long as it's continuous, there does have to be some x value where I hit the average value. Notice we even marked it here already. There is some x that when I plug it into the function, I spit out the value for the average y. Okay, so question number 3 here is just asking us to try and determine what that value of x is going to be. So I'll write out everything that we need in the following way. I'll say since f of x is a polynomial, it is continuous on the interval from 0 to 3. So I know that there must exist a value of c, like that the mean value theorem for integrals guarantees. So I'll even state that. So the mean value theorem for integrals states that there is a value of c in between 0 and 3, or possibly 0 or 3 themselves, such that my f of c could be equal to 1 over 3 minus 0 times this integral from 0 to 3 of my function f of x. That is my average value. And notice again that I'm just going to state this value as 5/2, or 2.5, since that's what we had already calculated back in example 1. Now, if I'm interested in finding the c that can do this, I'm just asking, what is the value of c I can plug into my function to get back 5/2, or 2.5? And what a challenging question that is. Notice, if I want this value of f of x to be equal to 5/2, then I can just write this. I'll say we see that f of x will spit out the value of 5/2 whenever 1 plus x spits out the value of 5/2. Which of course is when x spits out, or when x is the value 3/2. So the value of c is 3/2, or 1.5. Now, this looks like a lot of work, again, to answer a question that's actually really, really simple. I'm trying to write out a lot of the detail here to help continually narrate the idea. But notice that you could have almost just immediately deduced this, right? If I look back again and I say, what can I plug into this function to get the answer 2.5? You go, Kyle, you plug in 1.5. It's 1 plus 1.5. We're done. And yeah, I'm just showing the process here of how I would do this in more general terms, in case things get a little bit more complicated. And things do get a little more complicated down here on example number 4. Notice example number 4 is going to relate back to the function that we talked about in example 2. Let's take a look back at example 2 quickly to kind of see what we found there. Notice that in this example we were dealing with a half circle, and we found that our average y value was going to be pi over 4. And we actually found that there appeared to be 2 different x values where we would hit our average y. And so the goal again in example 4 is going to be to find these x values. So let's see. I'm going to go ahead here and first confirm that I do indeed have a continuous function here. Notice I have a root function, which should be continuous as long as the inside never turns into a negative number. However, since I'm only using values between -1 and 1, and -1 and +1 themselves, this at smallest will ever be 0 on the inside. So I can state here that since f of x equals the square root of 1 minus x squared is continuous on the interval from -1 to 1, the mean value theorem for integrals states that there is a value of c in the interval from -1 to 1 such that f of c will turn into my f average, which, remember, in this case is going to really just be equal to that value of pi over 4 that we found back in the previous example. So we can state here that we know that f of x here will actually be equal to pi over 4 when that would be when the square root, of 1 minus x squared is going to be equal to pi over 4. So can I solve for x? Sure. Let's see. I would square both sides. So 1 minus an x squared is going to be equal to, what is that, pi squared over 16. I just square the top and square the bottom. I could add the x squared over and subtract over the pi squared over the 16. So this will get me x squared is equal to 1 minus a pi squared over a 16. And then I could go ahead and, I could square root. And of course, don't forget when I square root here, I'm going to need plus or minus the square root of 1 minus a pi squared over a 16. Thus, my c, I actually have two different c's here. I'll call them c1 is this positive square root, and then c2 is actually going to be this negative square root. And again, this corresponds perfectly with what we saw in the picture, that there were actually two distinct x values. They were pretty close to -1 and 1, and you could even check these in a calculator. They are pretty close to -1 and 1 respectively. Or, 1 and -1 respectively. But these values were both values that if I plug them into the function, I get back the value pi over 4. In fact, it's actually even really easy to see that you could just directly plug these back in. If I square them, the square root gets removed. And then I would have to distribute my negative. That would turn the 1 to a negative and this to a positive. And then the 1s would cancel. I square root the pi squared over the 16. I'm back to pi over 4. So both these values here end up being acceptable. So using the mean value theorem for integrals is just, again, an easy way to confirm or to demonstrate that there must be values where I hit the average value. And we'll see how we can use that kind of in a more general sense when we take a look at example 5 in the next video.